What's going on, everybody? In this video, we're going to be talking about definite integrals. Now, the main idea here is that when we were finding derivatives, right? Derivatives gave us the slope. But what do integrals give us? Well, that's what we're going to find out in this video. So, we're going to do some work here with definite integrals, the fundamental theorem of calculus, and I have all the timestamps on the left. But to be a little more specific about what topics we're going to be going through in this video and what kind of practice we're going to be doing, I'll scroll through the notes real quick and just talk a little bit about each section. So first I'm going to give you an introduction. This is going to start introducing how the integral actually gives us the area under a curve. And then we're going to do a really nice example with velocity and position, and it'll show you exactly how that works. Now we will get into the notation and the nomenclature of indefinite versus definite integrals. I just want to show you how they're different, especially, with just being able to at least identify which one's an indefinite, which one's a definite integral, right? The main thing right away is that a definite integral has bounds, right? These numbers right there on the integral symbol. And we'll talk about some other differences, especially with the naming. We'll get into the fundamental theorem of calculus part 2, and the idea with this section is, well, okay, now we've got through all the intro stuff. How do we actually use an integral to find the area under a curve? And so what we're going to do is we're going to actually figure out that we can do that using the fundamental theorem of calculus part 2. This is how we're actually going to evaluate definite integrals. Okay, and so we're just going to use that formula. I promise it's pretty nice and easy compared to some other stuff that you've done in calc so far. And then we will do some practice quick with definite integrals using the fundamental theorem of calculus part 2. Okay, and if you're wondering, I'm doing part 2 before part 1. I know that's kind of, it seems backwards, but the reason why is because you can't fully understand fundamental theorem of calculus part 1 until you understand part 2. And so I feel like the way that the fundamental theorem of calculus is taught is kind of switched. I think it should be part 2 first, but that's just my opinion there. You'll see later in this video why you can't understand the fundamental theorem of calculus part 1 until you get part 2, but just wait on that. So then I want to get into a section about how integrals actually equal the area under a curve. I want to really unravel what's going on here. And so I'm going to talk a little bit about Riemann sums. I'm going to talk a little bit about this rectangle approximation method to find the area under a curve from A to B. Right? And I'm going to talk about how you can approximate it with rectangles, and that what an integral does is it's essentially an infinite number of these rectangles in this space. And so your guess, your estimate, becomes infinitely accurate, right? And so that's what an integral really does. And that'll also help understand the notation, like what the dx means, what the integrand is actually doing, all that. And by the way, the integrand is like the f of x. It's the function that you put in the integral. Okay, then we're going to go through some quick integral properties. This isn't going to be anything, the first two aren't anything new. Constant multiple rule and sum and difference rule. We've talked about that in indefinite integrals, and you've also done that with derivatives. But then there's going to be some new rules that we introduce, and they're really not going to be anything too complicated. I promise. I'll be able to explain them using area under a curve. And then there's some symmetry stuff that we can do with odd and even functions and periodic functions as well. Like, periodic meaning like sine, cosine, all that. It's just, we can really simplify integrals when we know that the thing that we're integrating is like an odd function like x cubed or an even function like x squared. There's a lot of times where we can simplify and things get really nice. So we'll do some practice with that, and then the last thing we'll do is get into the fundamental theorem of calculus part 1. And essentially what this says is that a derivative is going to cancel out an integral. So if you take the derivative of an integral of a function, it's just going to give you back that function. And again, the reason for this is because a derivative and a integral are opposites, right? A integral is a reverse derivative, right? Remember, we introduced things like reverse power rule in the indefinite integrals video. It's that idea. Now, there is more to this, of course. You're probably wondering, okay, why are your bounds a and x and not a and b? And also, why are you using t here? I'll get into that. And of course, then we'll do plenty of practice with that, especially practice that's really gross that I always had trouble with when I was in Calc 1. And, like when you have x squared and x cubed is the bounds, like what do you do then? So we'll all be getting into that in this video, okay? And of course, as always, I do have the notes for this video, the unfinished and finished notes, listed as PDFs in the description below. Now, before we get into this video, I do quickly want to mention my full Calc 1 course, which I'm going to have linked in the description down below. In this course, I have plenty more practice problems to really get you feeling confident with each topic. I also have video explanations for every single practice problem in the course, so don't worry, you won't be left in the dust on anything. And so, if you're interested in that, be sure to check out the link in the description down below. Now let's get into this video. So I want to start here with that introduction. And the main idea here is that, again, the derivative gives us the slope of a function. We've done a lot of practice with that, using the derivative to help us find what the slope of a curve is at a specific point or anything like that, right? The derivative function is our slope function. Now, the main point that I'm trying to get across here is that the integral, the opposite of a derivative, what does that do for us? You know, here we have like a nice representation of what a derivative does that we can like visualize, right? It gives us the slope. What does the integral do? It gives us the area under a curve. Okay, and so I'll give you a quick example here that shows this, and this is probably the first example you would learn, and that's using velocity to calculate position, right? For example here, this problem you can probably figure out without using any calculus at all. This is pretty quick. If I'm moving if I'm moving with a velocity of 5 meters per second, how far have I moved after 4 seconds? Well, to find that out, you know, you could either use the formula that you learned in physics, that your distance equals velocity times time, or you could just kind of figure that out, right, with unit conversion or whatever. If I'm moving at 5 meters per second for 4 seconds, oh, well then I've moved, 20 meters, and you multiply them together, right? But I want to show you 2 other ways that you can find this, and it ends up being the same idea of 5 times 4. Okay? The first way you can do this, that 20 meters, is actually going to pop up as the area under a curve, and that curve being your velocity time curve. Okay? If I set up a graph for velocity versus time, I know that my velocity is 5 meters per second for every time, right? So I'll make a line here for 5 meters per second. Right, this will be v equals 5. And then we're going to cut this off at t equals 4. Right? This is going to be the time elapsed. And so watch what happens here. Underneath this curve, and I'll write this in white so you can really see what the curve is, right? The curve is this guy. If we look at the area under the curve from 0 to 4, and the area under the curve, meaning the area, it's bounded by the t-axis in this case, right, the horizontal axis. We don't go below it. That wouldn't really make sense, because then you would end up with like an infinite area. But this area bounded by the curve, what is it? It's a rectangle, and this rectangle has a length of 5, a length of 4 and a height of 5. And that gives us 20. And you could put units on that too, right? T is in seconds, so this is 4 seconds. V is in meters per second, so this is meters per second. And so when you multiply those together, again, the seconds cancel off, you're left with meters. And so I understand that it's probably pretty weird for you to have an area represented as a distance, but realize here that these aren't 2 regular spatial dimensions. And I know that's some big words there. What I meant is, it's not like this is your x direction and this is your y direction, and what you've just found with that area is a distance. No, we're talking about velocity, which is not like position. It's not like an x direction. And we have t, which is time. That's not like a y direction. These are different types of units that we're dealing with. So, of course, distance and area, they're going to mean different things on different graphs. Okay? Awesome. So we get that area under the curve is 20 meters. And I want to show you that you can also find the area under a curve using an integral. Okay? Because, of course, the problem is that what if you don't have a flat line where the area is a nice, easy rectangle? What if you have a graph like y equals x squared, and you're trying to find this area right here? Okay, that's not a triangle, right? That's a curved line. So how would you find that? Well, you can actually use an integral. But I want to at least show you that you can find the area under a curve with this example. Now we know that our velocity function is 5, right? We know that here. The velocity is 5 for every single time t. So what we can do is we can integrate both sides, because the integral of velocity is position. Okay, so we're integrating here. Right, you should know that the derivative of position is velocity, and so when we go backwards, the integral of velocity is position. So we integrate this side here, and we're going to get our position function, which we'll call x of t. Okay? And then if we integrate this guy, this is like a 5 times t to the 0 power, right? T to the 0 is 1, or actually you're probably a little more comfortable seeing this as an x. So separate this from this example here, and we're just going to use a different variable here, a variable that you're probably more comfortable seeing. If I do reverse power rule on this, I raise the power by 1, so instead of being a 0, this is a 1, and I bring this power out front and I flip it. So instead of being a 1 over 1, well, I guess if we flip it, it's still going to be a 1 over 1, right? So we get a 1 over 1 out here, which doesn't do anything, it's just 1. And so we get that the integral of 5 is going to be 5t. Instead of x, we're just going to have a t, and that, of course, is to the first power. Okay? And so whenever you see a constant, just tack on that variable on the end, and that's how you integrate it, okay? Just want to give you a quick refresher on that. Of course, we're going to add our plus c at the end, but I want you to understand what the actual meaning of that plus c is here. The plus c, if you just look at your initial position, right? What's your position at time equals 0? Well, that's going to make this go to 0, right? We're just plugging in a 0 for t. And then we get that our initial position is c. But let's say our initial position is 0, so that means c would be 0 here, because that just makes sense. We're starting from x equals 0. Let's see where we end up. And so if we make c 0, then this entire piece goes away. Okay? And then we get that our position after 4 seconds is that 5 times 4. That's 20. And so you see there's this interesting relationship here between the integral and the area under a curve. And we'll explore more why this is when we get later into this video. But for now, let's focus on the notation. Okay, I just want to talk to you a little bit about how indefinite integrals are different from definite integrals, right? Because with indefinite integrals, it seemed like our only goal was just to, reverse derivatives. And now it's like, okay, yeah, we're finding the area under a curve now. So it feels like there's two different things going on here. So let me just kind of bring it all together here and tell you the big picture of what's going on. So with an indefinite integral, okay, with an indefinite integral, we don't have any numbers on that integral symbol like we do here. Those numbers are called bounds, and I'll talk about that in a second. But what the indefinite integral did was, if we integrate something like this, we get something like this position function right here, okay? This function doesn't give us the area under a specific part of the curve. This function gives us something that we can use to find the area under a specific part of the curve, like we did in the next step, right? In the next step, we used that function to find the area from under the curve from 0 to 4. Okay, but as this sits right now, this is indefinite, meaning that the part of the curve that we actually want to find the area under is not defined. Right? We need to get to this part in order to now, use it to find whatever part of whatever area under the curve that we want to find. Like for instance, we could have, drug this out another number. We could have, looked at the distance I've traveled after 5 seconds. And now we just plug in 5 instead of 0, or instead of 4, right? So basically the indefinite integral gives us that initial function that we can now use to find the area, okay? The definite integral takes this one step further. What a definite integral would do is it will tell us that, oh, yeah, you want to do the regular indefinite integral, and now you want to use that function that you're going to find. You're going to want to use that position function that you get when you integrate, and now you're going to use it to find a specific area. Here it would be the area from x equals 1 to x equals 2. So it would be finding this area here. Okay? That is the big difference. Okay? So the indefinite integral says stop here. Stop at this, I guess you could even call it an area function. It's a function that can now give you the area under whatever part of the curve you want. But the definite integral says go one step further and actually find the area, and it specifies where it wants you to find the area, right? It talks about, it is a definite integral. Where you want to find the area is defined. Okay? So that's the main difference there. All right? Now, moving on to the Fundamental Theorem of Calculus, Part 2. Okay? How do we actually use an integral to find the area under a curve? All I've said so far in this video is that, oh yeah, an integral is related to the area under a curve. But how do we actually go and find this? Yeah, in this example, we were able to find it from 0 to 4. Right, we were able to find that area under a curve. But what if I wanted to find it from 1 to 4? What if I wanted to find this area instead of that area from 0 to 4? How would I do it? Well, let's think about this. Let's get rid of this for a second. Okay, and let's find the area from 1 to 4. And to do that, we need to understand, well, what is the position function giving us when we plug in that 4? Well, it's giving us the area from 0 to 4. So how do I find this area? Well, why don't we plug in 1 next? And if we plug in 1, you get 5 times, plug in 1 to this t, right? We get 1, this is 5. And now what we found, we have the area of this entire piece right here. That's what we get when we plug in 4. But when we plug in 1, we get just the area from 0 to 1. So can you see what we have to do to get this piece? Well, think about it. This piece plus this piece is going to give us the entire x of 4. It gives us that entire area. So if we take x of 4 and we subtract x of 1, we get, if you want to call it this, the integral from 1 to 4. The area under this curve from 1 to 4. Okay? And it's the area of the velocity curve, which actually ends up here being, remember, so it's v of t right here. But we know here that v of t is, actually, I'll just write v of t. V of t actually is 5 here, of course. But I'll just be a little more general and I'll write v of t. But that's what we get here. Okay, so we integrate it, right like an indefinite integral, we find that position function. And then we plug in x of 4 to get that total area, and we subtract off this little itty bitty area from 0 to 1 to get the area from 1 to 4. Okay? And that is basically what the Fundamental Theorem of Calculus Part 2 is. Instead of, let's get away from this whole velocity and position thing, especially if it's starting to confuse you a little bit. What I wanted to do is give you kind of a real-world example of this, but if we want to be a little more general, instead of using v, let's just talk about a regular function f. Okay? We'll integrate some function. This could be x squared, x cubed, whatever. And what it says is we're going to integrate it. And we're going to get a function, the function that we get when we integrate f I don't know if you've ever seen it written like this before, but when we integrate f, this is supposed to be a different thing, we get capital F of x. That's what we call our antiderivative function, or our integral. We call it capital F of x. Okay, and so what we do, so actually, let me explain that a little further. Like if f of x was x squared, we use reverse power rule and we get this. This would be 1/3 x cubed. Okay, so that's the relationship between these two. And so what we do is we find that capital F of x function, which here would be that position function. And we're going to plug in the upper bound. That's what that's called. And then we subtract the lower bound. And that's exactly what this is doing. Right? That's exactly what is going on here. It's taking that big area, it's subtracting off the little area, and giving us the area that we want to find. Okay? And so a little more generally, let's say instead of having 1 and 4, we have a and b. Well, now it's capital F of b minus capital F of a. All right? And so that is what the Fundamental Theorem of Calculus Part 2 says. So let's do a quick practice problem with this. I promise this is going to be a lot quicker than all the conceptual explanation stuff. I mean, I try to, make that as simple as I can and try to relate it to velocity and position because it's something you've worked with a lot with derivatives. But really, actually going through and doing this is a lot simpler than trying to explain the conceptual stuff. Let me show you. Let's just do this integral quick, okay? Forget about the bounds for now. We'll worry about those later with the Fundamental Theorem of Calculus Part 2. And I promise, they won't actually be that bad. Let's just worry about this part first, just the regular indefinite integral, okay, without the bounds. So how do we integrate this? This is a reverse power rule, right? We just reverse power rule this, this, and then this. If we reverse power rule x squared, we've done that before, we get 1/3 x cubed. Or you could write it as x cubed over 3. If we reverse power rule 2x, well, let's think about that. We're going to get a 2 times x. We raise that power by 1. So instead of being x to the first power, it's going to be x squared. Instead of this power being 2 over 1, when we bring it out front, it's going to be a 1 over 2. We flip it, right? And that's what reverse power rule says. Raise the power by 1, bring it out front, and flip it. Okay? And then remember, when we have a constant by itself, we're just going to tack on an x there. Okay? And then we're not going to worry about plus c's here. I mean, you can if you want to, but actually, let's even do that here. I'll put in the plus c. I'll show you that it goes away. Okay? But now I'm going to tack on an evaluation bar. That's what this thing is. It's the only little bit of notation that I haven't talked about yet. What this means is that this antiderivative, this integral, is now ready for us to use the Fundamental Theorem of Calculus Part 2 on it. It's ready for those bounds to be plugged in and for us to find that area from 1 to 3, from x equals 1 to x equals 3. So that's why we put the 1 and the 3 there. Okay? And so, what does this theorem say? Well, it says that to find the value of this integral, we're going to take the antiderivative function, capital F. Capital F is this guy. Okay? And we plug in the first bound. That's what the little b says. And I'll make this a little bit bigger if you're having trouble seeing it. How about that? Okay? We're going to plug in b. That's b. So let's do that. We get 1/3 times 3 cubed plus this guy just becomes a 1. So you have just this x squared, and x squared is going to be 3 squared. Then we get minus 4 times 3, and then we have the plus c. Okay, and actually, instead of using parentheses here, I'm going to use brackets because we're using parentheses inside there. Okay, and so that right there is f of b. Now we're going to subtract f of a. That's going to be the exact same thing, but now we're plugging in 1. And so we get 1/3 times 1 cubed plus 1 squared minus 4 times 1 plus c this guy's capital F of A. Okay? Notice right away that the c's go away, right? When we try to simplify all this and we combine all these terms, okay, we get a c minus a c. And so the c's go away. And when you're doing definite integration, you don't need to worry about the c's. Okay, just forget about that. The only time where you really care about using the plus c is going to be in indefinite integration. Okay. So let's go through and do this here. 1/3 times 3 cubed. Well, 3 cubed is 27. Divide that by this 3, and you're going to get 9. Then you get a 3 squared. That's 9. Negative 4 times 3 is negative 12. And that's going to be it for the first bracket. Then we have minus. This is a 1/3. Then we're going to get a plus 1 minus 4. And that is something that we can work with here. And so now let's just combine all this together. 9 plus 9 is 18. Minus 12 is 6. We get minus. Then we have a 1/3. And then here we have a minus 3. So we can find common denominators here and get that the 6 can be 18 over 3. And then we get this 1/3 is going to stay. Oops. Glitching. Okay. And then this 3 is going to become a 9 over 3. Okay. And so we can combine like terms on the inside of this, or not combine like terms. We're just combining. They're all the same term. But we're combining inside that parentheses to get negative 8 over 3. And then we get 18 over 3 minus a negative 8 over 3. These become positive, and you're left with a 26 over 3. And so really all that's happened here, okay, all that's different from what we've been doing, right? This is what's similar. This is an indefinite integral, and we found what the value is right here. We integrated, that was it. Then we used the Fundamental Theorem of Calculus part 2. We did the f of b minus f of a. This guy right here, that function, is your integral function. That is capital F of x, right? If you get rid of this, right? That is capital F of x. But now we evaluate that thing. Okay, that's what the evaluation bar says. It says we still have to do this step down here. We still have to do the f of b minus f of a. Okay, it says we're ready for it. And we do that. First, we plug in the upper bound, the taller one, or the yeah, you get what I mean when I say upper bound. And then you subtract that same function with the lower bound plugged in. Okay? And then that's really it. So now that we've done some practice evaluating definite integrals, I want to move on to this next section, which is how integrals are actually giving us the area under the curve. Okay? There is a lot of conceptual stuff in this video, and I didn't want to like put it all in the beginning. I wanted to spread it out a little bit because, you know, having just a professor or a teacher talk just conceptual stuff for, 30 straight minutes or 40 straight minutes. I've been in classes like that. Well, even classes where it's like an hour and a half of just that. And that gets really old really fast and just really hard to stay with and all that. So I wanted to put some practice in there just so you start understanding how these problems work. And now I'm going to hopefully clear up for you why an integral is giving us the area under a curve. I want to show you what an integral, what taking these reverse derivatives is really doing for us. So what we're going to do to start off this section, okay, it's really quick. We're going to start by estimating the area under this curve from x equals 1 to x equals 4. Okay, so we're going to start from x equals 1, and then we're going to go to x equals 4, and we're going to estimate what this area actually is. And there are three main ways that we go about estimating this area. And they're all called Riemann sums. They're just three different types. The three different types are called LRAM, MRAM, and RRAM. And I'm not going to do full examples of these or anything like that. I really want to focus on definite integrals in this video, but I will talk a little bit about what these are. LRAM is a left-handed Riemann approximation method. MRAM is a middle Riemann approximation method, and RRAM is a right-handed Riemann approximation method. Okay, so what's the difference between L, middle, and right? Well, the difference is that when we're going to divide this area up into rectangles in all of these guys. Okay, that's how we're going to do this estimation. We're going to divide these area into rectangles, and we're going to add up the area of these rectangles. Okay, but with LRAM, when we divide these rectangles, okay, the left side of the rectangle is going to touch the curve. And maybe to make this a little more clear to you right now, I won't fill in these sections. How about that? Okay, see now that the left part of the rectangle is the one touching the curve. In a MRAM, when you make all these rectangles, the middle part of the rectangle is touching the curve. Okay, and then in a RRAM, when you do this estimation, it's the right side of the rectangles that are touching the curve. Okay, in different ones, you can see that with an RRAM, we got a lot of over approximation going on, right? We're way over. With an MRAM, we're getting a little over approximation, a little under approximation. And with LRAM, we're getting a lot under the curve, right? That we're missing a lot that's under the curve. Okay, so that's really what's going on with all this. But for the sake of this example, I'm going to do an LRAM. Okay, I'm just going to do an LRAM here. We're going to talk about it quick. And let's see all the area that we get. So we'll just go right here. Okay, there's another rectangle, and then we'll do our last rectangle here, over to 4. There you go. Okay, and so the left corner of the rectangle is going to touch the curve every time. And we can add up the areas of these rectangles pretty easily. Okay, we know that, first off, the length of all these rectangles is 1. And what about the height of these rectangles? Well, the height of this first rectangle here, I need to use a different color. I hate to use it like yellow in a blue section, but it's going to help point this out. So the height of this first rectangle is going to be the y value, f of 1. Okay, when you plug in x equals 1 into the function, it's the y value that you get out, right? And that is going to be the height of that first rectangle. Okay, what about the height of the second rectangle? Well, when you plug in x equals 2 into whatever function you're dealing with here, whatever function is giving you this curve, that's going to be the height of your second rectangle, right? And then you have your third one, and that's going to be the height of the height of the third rectangle is going to be f of 3. Okay, and just like that, if instead this rectangle was an RRAM and we had the right side touching the curve, like that, well then the height of this last rectangle would be, can you guess it? It would be f of 4 here. Okay, because that is where we're touching the curve. That's the y value. Okay, and so here we have our estimation, right? We're able to add up all these areas here and get close to what the area of this entire thing is, but it's not exact. And so how do we make this estimation better? Well, we can add more rectangles. That's the question I have here. What would happen to the accuracy of our estimation if we add more rectangles? And let me show you. It would essentially be this guy right here. Okay, here I've done twice as many rectangles. So you can see here from 1 to 2, I have 2 different rectangles going on here. Okay, and from 2 to 3, I have another 2 rectangles and all that. And so, let me move this over. I'll show you the difference here. Okay, how will I bring this down now? I will duplicate this guy, make it smaller, bring it down. Okay, you can see here that when I double those rectangles, look at how much smaller all that missed area gets. Right? There's not much missed area compared to all the missed area we have here. Right? We're able to fill some of that missed area with that next rectangle. Right? And now we only have this much and this. But it's much less than what we originally had. Okay? And so, well, how do we make this estimation the actual value of the area under the curve? Well, we would have to have an infinite number of rectangles. So our estimation becomes, the actual value. It becomes infinitely accurate, if you want to say it that way. And so, well, that's exactly what an integral is doing. An integral adds up that infinite number of rectangles. And, well, that gives you the actual area under the curve. I'll show you this with the limit definition of what a definite integral is. We've done the limit definition of a derivative. This is the limit definition of an integral. Okay? That's what's going on here. This is where this thing is coming full circle. So what we're going to have here is that we're trying to find the integral from a to b of this function. Okay? We've done stuff like that before. Now this limit gets a little nasty, but if you look at this one at a time, it's actually not that bad. Okay? Here's what's going on here. We're going to divide this up into this area, this segment here. We divide it up into, pretend there's like an infinite number of rectangles here. Okay, this is going to be A. This is going to be B. I'll use a smaller marker here so it don't, there we go. So this is going to be x1. We're going to call this x2. This will be x3. Right, and each time I'm going over an x, I'm starting a new rectangle. And we keep going here, and we eventually end up at our last rectangle, which is going to be x sub n. Okay? And so you can imagine that as we get an infinite number of rectangles here, this value of n, our last rectangle, is going to become infinitely large. It's going to go to infinity, right? And that gives us our infinite number of rectangles. N is actually what that's what that means. It's the number of rectangles that we have. And so we take the limit as n approaches infinity. Okay? And then all this sum is it's adding up the area, right? A sum is adding a bunch of terms, and all those terms are the areas of these little rectangles here. Okay? You can see that. This right here is the height, and this is the width. Delta x is the width. That should make sense, right? That's going to be these little guys right here. Okay? But what is this f of xi? Well, we're going to call this one here, and this little index down here, we call that x sub I. Okay? And that x sub I in the summation is going to go from, it's going to go from I equals 1 to n. So it's going to go I equals 1, I equals 2, I equals 3. And so it's going to give you x1, x2, and x3, right? That's how the sum works there. And so as it goes, it's going to add all those terms. It's going to first give you, like here's the first term of this series. It's going to be f of x1 times delta x. What is f of x1? Well, we've talked about that. That's going to be the height of this first rectangle, right? F of x1 is the y value at x1. Okay? And then you have your delta x. That's going to be the width of this rectangle. Okay? The next term in the series is going to be f of x2, because now you go from I equals 1 to I equals 2. Okay? And so this I becomes a 2. And then you multiply by delta x again. The delta x just stays the same, right? It's a constant. It's just going to be the width of your rectangles. And that delta x is going to go to 0. Okay? And so you can see, where the terms would go from here. It'd be f of x3, f of x4, blah, blah, blah. Okay? And so now that we've talked about the height and the width of these rectangles, I want you to realize that that exact thing shows up in the actual integral itself. And those meanings transfer, right? The width of each of your rectangles becomes infinitely small, because that's the only way you can fit an infinite number of rectangles in this area here. You have to make the width of each of them infinitely small. And when we move an infinitely small distance in the x direction, that's that differential, that's the dx. We turn that delta x into a dx. Remember how the slope, we used to call that delta y over delta x in algebra, right? But now in calculus, we would call that the derivative, right, dy over dx, because we're moving an infinitely small distance across an infinitely small distance up or down, right? That would give us our dy over dx. So dx is that infinitely small nudge. It's the width of each of those rectangles. And f of x is the height. And when you combine a height and a width, you get an area. And so what this integral symbol does is it essentially is gonna sum up, you can think of it as summing up all those different areas. Okay, that's how I like to think about it, right? Here's your width, here's your height, and here's the thing that sums them all up, is taking the integral. All right, so that's really what's going on here. That's what a definite integral does. Okay, great. So now that we've gotten through that, let's get into some integral properties, and these are going to actually help you in your everyday definite integrals. These are actually going to help you in the practice problems. It was just hard to get through all of that conceptual stuff in the beginning of the video, but if you got through that and you feel somewhat comfortable with that, this stuff is going to fly right through. Okay, so integral properties. First off, constant multiple rule, sum difference rule. They're the same as with indefinite integrals, right? And also the same with derivatives. We can pull a constant out. The constant doesn't matter. If it's being multiplied, we can pull it out, it's fine. Sum and difference rule. If we have two things being added or subtracted, we integrate them separately. And we do that anyways. Like for example, with the green section, we integrate the x squared and we get this. We integrate the 2x, we get this. Integrate the 4, we get this, right? And so we're already separating them. We're just not writing them as they're each of them having their own separate integral. Okay, but really, technically, this is what's going on. Now, there's three more rules that I want to talk about, and that's the same bound rule, the area sum rule, and the bound swap rule. The same bound rule is probably it might be the easiest to understand out of these. I mean, they're all pretty all right, especially these two. The same bound rule says that if you're trying to find the area under a curve from like x equals 2 to x equals 2, these are a's, okay? They're not 2's, but because I know sometimes people mistake my a's for my 2's. But let's say you're trying to do that. You're trying to find the area from 2 to 2. That really doesn't make any sense, right? This is a line. This doesn't have any area when you pick the same bound both times. And so since a line doesn't have any area, your answer is 0. That's the same bound rule. Now the area sum rule is something we've actually already done in this video. Okay, it's actually a little bit about the Fundamental Theorem of Calculus part 2. I can bring that up here. Think about it. If we would have said here the integral from 0 to 1 of our velocity function plus the integral from 1 to 4 of our velocity function, we would be saying, okay, let's take the area here, that's the area from 0 to 1, and then add it to the area from 1 to 4. What do we get? Well, we get the total area from 0 to 4 of this guy. Right, that's exactly what the area of sum rule is. Like literally, that's it. It's just that. Okay, let me get back down to the rules here. Okay, and you can see that here. You can just split that guy up from A to C into A to B and B to C. Now the bound swap rule, this one is actually, I mean, I feel like a lot of people just don't understand why this happens. The integral from a to b is equal to the negative integral from b to a. Like if you switch your bounds, so your lower bound becomes your upper bound and your upper bound becomes your lower bound. And I did wonder why that was for the longest time, but the reason why that is because think about your let's have your x and y axes here, okay, and let's have your curve. If you were integrating from a to b, here's the process, okay. Here's a, here's b, here's the area you're trying to find, okay. Now when you're trying to integrate this, here's how you do it. Well, you move over a little dx, right? Or a little, let's say a little delta x, right? And that delta x is positive. Of course, you then take the height of this little rectangle and then you multiply them together, you get the area of this guy. And then you move on to the next rectangle, right? And you're moving right until you get to b. That's how the integration process works. Right, it's kind of like rectangle by rectangle. They're like building blocks. But what happens if we're going from b to a? That's exactly what the integral said right here. Now we're going from b to a. Well, here's what happens. The rectangles don't start from left to right anymore. We're going from b to a. And so you start going like this. Now what that means is that the delta x is negative now because you're moving left, you're not moving right. And so if all these delta x's are they're all negative, now you get a bunch of negative areas that you're adding all of them up, right? And so it would be the negative version of the integral from a to b, okay? So it's going to be the negative as if you went this way. That's exactly what goes on there. Now for that same reason, and so of course just think that, for that same reason, that's why any area that you have underneath the graph, we actually call that negative. Okay, so if you had a graph like this, actually I'll draw the graph like this, how about that? And I go like that. All this area right here is positive, and all this area here is negative. The reason being because the height of all these rectangles is positive, right? But the height of all these rectangles, they're negative. Like let's say this rectangle goes down to y equals -1, and this rectangle goes down to -2, right? And all that. Of course, I'm not really drawing rectangles here. If I was, it would look like this. But you get what I'm saying, right? That's really what's going on here. Okay, all these rectangles have a negative height, and so the area is negative. Okay, so that's really what's going on with that. But yeah, there's all your rules, and there's, if you want to take a screenshot, I'll zoom out there for you. Okay. So then there's also some symmetry properties, and these go off of exactly what we just talked about with the whole negative area thing. For odd functions, what's something nice about an odd function? Well, think about x cubed. Okay, let's think about that graph. X cubed looks like this. And it's symmetrical. The area under the curve right here is going to be the exact same as the area under the curve. Let's see if I can draw it here. Like that. Those are the same, well, let's go right here. There we go. That's a little bit better of a drawing. Okay, so this area is going to match this area if, let's say, this guy is like -1 and this guy is 1, right? If we've gone out the same amount in both directions. And so, since the positive area matches the negative area, we say that the total area is 0 because they cancel each other out, okay? It's kind of like traveling in the left direction for 10 meters and then traveling back in the right direction for 10 meters. You end up back where you started, okay? That's really what's going on with that. And so if you see an odd function, like x cubed, right, or like a polynomial that only has odd exponents, okay, or actually something like sine of x, those are all odd functions. If you see something like that and you see that the bounds are from -1 to 1 or -2 to 2 or -3 to 3, the answer is 0. Now with even functions, it's basically the same idea. With even functions, now the area is going to match on both sides still, but it's both going to be positive, right? So this area right here is going to match this area. And so if you have the integral from -1 to 1 or -2 to 2 or whatever, you can just make this -a, or whatever it is, like -2, -3. You can make that guy a 0, and you can just double the integral, right? Bringing back my picture, that's like, you see that if I add this area to this area, it's the same thing as multiplying this area by 2, because these guys are the same thing. So that's exactly what we do. We just get rid of that area, and we say it's this guy times 2. Okay? And that is really nice for us, because when you get 0 as a bound, when you plug in 0 into a lot of these things, and you'll see that with some of the examples we do later, yeah, this integral becomes a lot easier most of the time. Okay, 0 is a nice number to work with. And so we could write this integral, the integral from -1 to 1 of x squared, we could write it as 2 times the integral of, we change this -1, we change that lower bound to a 0, and that upper bound stays as a 1. Okay, and so we add up 2 times of that right side area. So this is going to be the integral from 0 to 1 of x squared dx. Now the last type of symmetry that I want to talk about is periodic symmetry. This is something like with sine of x and cosine of x, all that. I know that I mentioned earlier that sine of x is an odd function, and I guess on that note, cosine is an even function. I'll show you that right now. Sine is like this, okay? And this area matches this area. So yes, they will cancel out if you do it like that. But there's a way that you don't have to have the -1 and 1 and -2 and 2 and -3 and 3 and all that to get 0 for this integral. Actually, for a periodic function like sine of x, if you just integrate it over one full period, like this, or even if you integrated it over 2 full periods, or whatever, if you're integrating it over like some multiple of periods, all these areas are going to cancel out. Right? You get a positive and a negative, a positive and a negative, right? And so that's going to work with any of these periodic functions that are, of course, I want to note here when I say that, these periodic functions are centered around the x-axis. Like if you had something like sine of x plus 1, well now this gets raised up, and those areas don't cancel out anymore. But they will if they look like this. Right? If you have something like this, then you have different stuff going on. Okay? So, for instance, okay, 0 to 2 pi of sine of x, that's one full period of sine, and that gives you 0. All right? And I want to note, I should have noted this at the beginning of the symmetry section, but you don't have to know any of these, okay? It's not going to make or break you. But it is a big time saver if you do know these. And so that's why I recommend just, looking them over from time to time. We'll do some practice with that right now. It'll just give you, a good idea of, ways to help you evaluate integrals even faster, because that is something that, you're going to want to do in the future, especially if you're taking Calc 2. You're going to have to be evaluating a lot of integrals. So, yeah. So we'll do some practice right now. And let's do an example where we do the integral from -pi/2 to pi/2 of cosine of x. Now we know that cosine of x is an even function. Okay, we're not, by the way, this integral is not over an entire period of cosine or something, so we don't have anything like that. But, cosine's like this, right? It goes like this, this. It's an even function. It's got the same stuff on this side as it does on this side. And so if we are going to integrate this thing from negative pi over 2 to pi over 2, we can just do 2 times the integral. Actually, I'll write this over here. We can do 2 times the integral from 0 to pi over 2. Okay? And that's of cosine of x. That's the whole idea with this even function thing I talked about. Okay, just think about that y equals x squared case. And so yeah, that's a really, really nice integral now for us because we have 0 in it. It's not going to matter that much with trig functions, but it's going to be still nice to have a 0. So we can integrate cosine of x to start integrating this now. And if you integrate cosine of x, you get sine of x. Okay, remember that 2 is in front of it, so we're going to have 2 sine of x. And now that we've done the indefinite integral part, now we have to worry about the bounds. To do that, we use the Fundamental Theorem of Calculus part 2. We put an evaluation bar here from 0 to pi over 2, and then we use that FTC part 2. You don't have to include the 2, you can just distribute it through at the end. So I'll do that now, but you can, of course, put the 2 in there. It's up to you. But here we're going to get sine of, we're going to put in our first bound, and then we're going to subtract sine of our lower bound. Okay. We know that sine of pi over 2 is 1. We know that sine of 0 is 0. So this guy is actually just going to be equal to 2 times 1, which is 2. All right, and so this is, less of an extreme example. You could still evaluate that integral just like that with the integral from negative pi over 2 to pi over 2, right? And then you would just have, if you did that, you'd have sine of x evaluated from negative pi over 2 to pi over 2. And then you would, instead of having a 0 here, you'd have negative pi over 2, the 2 would go away, all that stuff. Okay, but it's completely, up to you. It sometimes is a little bit faster if you do it this way. So then we have our next example here. And for this example, we have 3 integrals here. The integral from 1 to 0 of x squared dx, plus the integral from 0 to 3 of x squared dx, and the integral from 0 to 2, or from 2 to 2, of x cubed dx. First off, we know that since these are the same bound here, this integral is going to be 0. For this guy, the bounds are switched. And like I said, I was going to show you this. You can integrate it this way. You know the integral of x squared dx is 1/3 x cubed. We've done that integral a million times. And you can evaluate it from 1 to 0. What that would do, well, let's see. You would have 1/3 times, you plug in the first bound, the upper bound, and then you subtract 1/3 minus the lower bound. And so you get that this integral is, this guy's 0, and then this guy right here is negative 1/3. So that is indeed the value of this integral, but at the same token, you can switch this and make it a little more normal for yourself. It also helps eliminate the possibility of mistakes here, because a lot of people, what they'll do is they'll just switch the bounds back in their head later, and that's a mistake that I've made, a lot of other people in my class made. So, just to prevent that automatic switching that you might do in your head later on, it's good to just switch them up. So we can write this as the negative integral from 0 to 1 of x squared dx, plus the integral from 0 to 3 of x squared dx. And now notice here, these two have the same integrand. We're integrating the same thing. We're trying to find the area under the same curve here. But notice what's going on here. This thing is saying, hey, let's find the area under x squared from 0 to 3. Let's find this area right here. And this guy is saying, let's subtract the area from 0 to 1. So let's take this area away. Well, what does this guy equal then? It's this entire area minus this guy. Well, it would be this area right here, right? And that area is from 1 to 2. And this is the area sum rule. This guy ends up being the integral from 1 to 3. Sorry if I said 1 to 2 earlier, I meant 1 to 3 of x squared dx. Okay? I should just, that should make sense to you. We're taking out the area from 0 to 1. And again, you could just evaluate this as is. You could integrate this, plug in the bounds, integrate this, plug in the bounds. Or you could just simplify this and make it only one integral. So I'm saying if you don't catch on right away, not a big deal. Let's integrate this x squared. We get a 1/3 x cubed, and then we got to evaluate that. We got to plug that into the Fundamental Theorem of Calculus Part 2 with our bounds 1 and 3. Fundamental Theorem of Calculus Part 2 says that we're going to do 1/3 times our upper bound cubed, and then 1/3 times our lower bound cubed. The upper bound is 3, lower bound is 1. We get, this is a 27 over 3 is 9. This guy is a 1 divided by 3 is 1/3. And we've actually done 9 minus 1/3 before in this video. That was 26 over 3. Okay? Or we did something like that. We got 26 over 3 before in this video. Okay? So that's a little work with some properties. Now we'll move on to the last example here, which isn't really properties so much, but it is a very common example that you can get when talking about definite integrals. Okay, and that's just to use shapes to find the area here. Like here you can see that if we're trying to find the integral from -4 to 4, the area under the curve from -4 to 4. And so we have two shapes that you can probably see. We have a triangle right here, and we have a semicircle right here. And so all we actually have to do to find the area under the curve, and I guess it's not even the area under the curve, it's the area bounded by the curve and the x-axis. You know what I'm saying? So that should clear it up if you're dealing with area that goes below the x-axis. So we'll take the area of this triangle here. That's going to be base times height over 2. So we get BH over 2. And then it would be plus, but here we're dealing with a area under the curve right here. And so we're actually going to subtract that area. So we're going to have minus the area of a semicircle. So the area of a circle is pi r squared. This is a semicircle, and so we are going to do 1/2 of that. And now we're just going to plug in some numbers. We know the base of this triangle is 4. The height of it is 2 divided by 2. Then we have minus pi times the radius of the circle is 2. Square that guy, divide by 2. And now plugging that into your calculator here, you can see this is just a 4 minus 2 pi. And that is going to equal negative 2.3 when you plug that in your calculator. So moving on to our last section for this video, let's talk about the Fundamental Theorem of Calculus Part 1. And the idea with the Fundamental Theorem of Calculus Part 1, just like I was talking about in the intro, is that a derivative and an integral are opposites. Right? These guys are on opposite ends of the spectrum. You take a derivative. If you want to undo that derivative, you integrate. Right? If you integrate to undo that integral, you take a derivative. Right? And so each of them are opposites. And so it shouldn't surprise you that if you have a function, you integrate it, and then you take a derivative of that, that just brings you back to your original function. Right? And so that's really what the Fundamental Theorem of Calculus Part 1 is saying on the surface level. That's really what it's about. But there is some different stuff about this that might key you in to thinking that maybe there's some more stuff going on here. For instance, you might look at this x, wonder why on earth do we have an x as one of our bounds? Also, why is t involved at all in this integral? And so that's what I want to talk about for the next couple minutes here. Okay? So we're gonna talk about all this. We're gonna answer these questions. So to start off here, what if we just had the derivative? What if instead I wrote the Fundamental Theorem of Calculus Part 1, instead of having a to the x and a t here, I had a to the b and f of x, right? So like probably how you would normally expect to see this Fundamental Theorem of Calculus Part 1, right? This is the integral that you always see, is the integral from a to b, and this is the function that you always see, is f of x, not f of t. Well, here's the problem. Let's actually evaluate this thing using the Fundamental Theorem of Calculus Part 2. And when we take the derivative of something, like we need to actually know what that something is. So I'm going to write that with brackets here. The thing that we're taking a derivative of is this entire thing. And so we're going to do what's in the parentheses first, in the brackets rather. So here, this is equal to the derivative of this integral. We know that from the Fundamental Theorem of Calculus Part 1, we take f of x and we integrate it, right? And that's how we find capital F of x. This is our integral function, right? So, for example, f of x would be x squared. Capital F of x would be 1/3 x cubed. And we take that uppercase f and we plug in our top bound and we subtract that same function, but now with our bottom bound plugged in. So that's cool. But now, let's take a derivative of this guy. You might notice a problem here. This derivative is 0. Isn't it? Because once you plug in a number, we're plugging in numbers. B and A are just going to be numbers like, 8, 4, 10, right? And if you plug in a number into a function, it's not a function anymore. It's just a number. It's like you output a number like 12, like 2. It's not something that you can... it's not something that you would like take a derivative of like 2x or 3x squared, right? It's just a constant. And so when you take a derivative of it, it's 0. So take a derivative of this guy, it's 0. Take a derivative of this guy, it's 0. Right? These are numbers, just like 12 or 8 or 4. So that's the problem with using this notation, because once we've already integrated it with a definite integral, you now make this thing a number, right? When you integrate a definite integral, you get a number, but when you do an indefinite integral, you get a function, and that function is capital F of x. So let's improve on this a little bit. Let's do the derivative from a to x of f of t dt. Now, I'll already spoil the reason why we have t's here. The reason why we have t's here, you'll see in a second, is because it's going to make it easier to see how we're plugging this x in. If I had x's, it becomes a little more confusing. So just like we did before, I'm going to take the derivative of this guy. Okay, and we're going to attempt to, cancel have that derivative kind of cancel the integral and get our function back. So let's say that this is equal to the derivative, and we do that integral. So if we integrate this guy, integrate f of t, we get capital F of t. And the Fundamental Theorem of Calculus Part 2 says we're going to take this and we're going to first plug in the top bound. So you see where this would have got confusing. If I would have had x's in here instead of t's, then I'm going to be like, oh yeah, well, let's plug in an x, and then wait, that, you're plugging in an x for x, and so people will get confused, and so that's why teachers do that. Okay, not that people don't already get confused with the Fundamental Theorem of Calculus, but hopefully, having the t's in there will help a little bit. So we plug in that x to start off with. So instead of f of t, we have f of x. And then we subtract capital F of our lower bound, which is a. Now, here we have a function, and that's why we plug in x instead of b. Okay, because x is an actual variable. B is just a constant. Capital F of a, though that's a is just a constant, and so you plug that into a function, you get like something like f of 2 or f of 0 or f of -1. They're all numbers, like I was mentioning before, like 2 or 4 or 6. So we take a derivative of 2 or 4 or 6 and you get 0. So this guy's just equal to, since this guy is 0, you're equal to the derivative of the antiderivative. And you see now how those things cancel off and give you back your f of x. And so that's really what's going on under the hood for this guy. That's exactly what we just solved. We just did this. Right? That's why we got f of x when we ended up. And that's why we have our x as our bound and our t's in here. Okay? Cool. So now we'll do some actual examples that you would see. You would see something like this, and it would ask you to, take this derivative. Well, let's do that. And again, to make this a little less confusing, I'm going to put in those brackets. Awesome. So now we integrate this guy. And when we integrate it, again, let's just call this function, let's stop worrying about this thing for now. We'll just let f of t equal 3t plus 2. Okay? When we integrate this guy, I'm not going to integrate this thing. I know we're going to get f of t, capital F of t. Right? And so this thing is going to be equal to the derivative of capital F of, well, instead of having a t, we have to plug in our bounds, right? So we're going to have f of something minus capital F of something. That first bound we plug into the first thing. The second bound we plug into the second thing. And now we take that derivative. We just did this. It's equal to capital F, or lowercase f of x. And so we get the derivative, how about this? This guy goes to 0 because it's just a constant. This guy becomes f of x. So where does the 3t plus 2 come in? Well, we can figure out what f of x is. All this is, it's the same function that we had before. It's the same function f. It's 3t plus 2. But now instead of having a t, everywhere we see a t, we're plugging in an x. And so this is equal to 3x plus 2. Okay. Now this is the long way to show this out, and you're going to want to show it the long way out to make sure you're not making any silly mistakes like you could make for the next problem. Okay, the next problem is going to involve some chain rule that you might not see coming, and I didn't see I'll show you this. So this example right here. Okay, this example would always get me when I was in calc because I didn't understand how to deal with different bounds like x squared and x cubed. And if I would have known a little bit more about how to use the Fundamental Theorem of Calculus Part 2 for this guy, I think this would have been a lot easier for me, right? Because this really just ends up being chain rule. And it's not just, you plug in the x. Because now we don't even have an x anymore. We have an x squared and an x cubed. What do we do now? Do you just plug in an x cubed and then plug in an x squared? It's not just like that, okay? It's not that simple. So let's do this the exact same way that we just did. Take a derivative of this guy. And, well, we'll start off by integrating this. We'll call f of t the square root of t to the 4th minus 2. All right? And when we integrate that guy, we're going to get capital F of t. And so this guy's equal to the derivative of what? Well, it's the derivative of capital F of something minus capital F of something. That's the Fundamental Theorem of Calculus Part 2. And what are those things? Well, those things are going to be x cubed and x squared. But here's where chain rule comes in. And you might not be able to see it. I know it's a little bit different because it's in the function notation. It looks weird. But there's chain rule here. Here we have a function, x cubed, inside a larger function, capital F. Right? This is like having y equals x squared plus 1 squared. And you would have to use chain rule to take this derivative, right? You'd have to do dy over dx equals 2 times x squared plus 1. You take that derivative as normal. And then you have to multiply by the derivative of the inside. That's 2x here. Right? And so this is going to be like imagine this guy. This guy is like capital F of x cubed. This guy is like the derivative of capital F of x cubed, which, by the way, I mean, f with a little prime there, that's going to be just f of x cubed. It's going to be this function with an x cubed plugged in. Right, x cubed plugged in for a t. And then you have the derivative of the inside. That right here, that's the derivative of the x cubed. That's the derivative of x cubed. Okay, I'm trying to, draw that example and show you what's going on. If that's confusing at all, here, let me make it a lot simpler. This guy is equal to, not even a derivative, we're just going to take this derivative now. Take the derivative of this guy. We're going to take the derivative of the outside and leave the inside alone. Then we're going to multiply by the derivative of the inside. The derivative of x cubed is 3x squared. Now, we take the derivative of the outside, again, leave the inside alone, and then multiply by the derivative of the inside. Oh, there we go. And so we get that this guy is going to be 3x squared times f of x cubed minus 2x times f of x squared. The only thing that we have to do left is actually figure out what the heck these things are. And it's not that bad, seriously. All f of x cubed is plugging in x cubed for t. And so we'll do that right now. We get that this is 3x squared times the square root of, instead of a t, we have x cubed, and that thing is to the 4th power. We have minus 2. And then we have minus 2x times the square root of, instead of a t, we have an x squared now. That's to the 4th minus 2. Okay, so this ends up being 3x squared times the square root of x to the 12th minus 2 minus a 2x times the square root of x to the 8th minus 2. And that's it. That's probably the hardest problem you would get for Fundamental Theorem of Calculus, part 1. To be honest, I don't think you would get anything more difficult than that. I don't really think of, I can't think of anything that would be more hard, or will be harder than that, right? All you do is you evaluate this thing using the Fundamental Theorem of Calculus, part 2, right? Just call your integrand f of t, and then you integrate it to get capital F of t. You just think about that in your head. Okay, cool, I have that now, once I actually go through with this integral. And now, I use the Fundamental Theorem of Calculus, part 2. I have this f, and I have this f. I subtract them. And then I put x cubed, the top bound, into the first one, x squared, the bottom bound, into the second one. And then you just use chain rule. Derivative of the outside multiplied by, derivative of the outside multiplied by the derivative of the inside, and then you do the same thing for the second piece. Subtract them. And then the only other thing we had to do here was figure out what those two guys were. And all that required was us using the same function, but now plugging in an x cubed and an x squared for t. Okay? That's what that problem involved. And so, yeah, I mean, in this video, there was a lot of notation. There was a lot of different stuff going on. Okay? But really, all the practice problems end up being is this stuff, Fundamental Theorem of Calculus, part 2, and that's it. If you understand the idea of what's going on, that just helps you, understand why you're even doing anything of what you're doing, like why you actually care about the area under the curve. Oh, well, it has actual real-world applications, like finding if you have a velocity curve, it tells you where your position is and all that stuff. So it is useful. I wanted to show you that a little bit, and also hopefully that helped it make a little bit more sense why we did some of the stuff that we did, like the Fundamental Theorem of Calculus, part 2 and part 1 as well. Okay, so lastly, if you're interested in that full Calc 1 course where we do plenty more practice problems, especially for something like this, because we did have to go over a lot of conceptual stuff in this video, definitely check out the link in the description down below for my full Calc 1 course. Okay, so that's going to do it for this video, guys. I'll see you soon.